Well, thanks so much, Flora, for presenting today. Thrilled to be able to host you. I'm hosting today from the traditional territory of the Gitumden clan of the Wet'suwet'en Nation in Smithers. I'd like to thank our financial supporters who make seminars possible. We have been able to expand our boardroom and our video conferencing capacities, as well as our hybrid seminar technology. So that's greatly in part due to the support of the Bulkley Valley Community Foundation, as well as the Bulkley Valley Credit Union. So very grateful to them. I'm quite excited about this presentation today. Dr. Flora Krivak-Tetley is a researcher, plant ecologist with a very diverse background. Currently, she is in Hanover, New Hampshire, where she's a lecturer in biological sciences at Dartmouth College. And as well, she is also working with the Gitineau and modeling alternative forest management strategies in British Columbia in the ICH. And that is the focus of her presentation today. So thanks again so much, Flora. Great to have you.
Yeah, I'm going to talk about a project I've been working on for the last several years in northern BC. And we're asking questions about how to manage forests for climate change mitigation in northwestern BC. So I wanted to acknowledge my collaborators on this project. They include Karen Diamond and Erica Lillis at the BC Ministry of Forests. We're working with Tara Marsden, with the Gitineau, and Bianca Eskelson at the University of British Columbia. And part of this work was funded by the Forest Carbon Initiative, so I'd like to acknowledge that funding source. So a quick little roadmap of what I'm going to talk about today. First, I'll explain sort of our project motivation and background, and then I'm going to present results on landscape scale carbon modeling that we've been doing. And I'm going to present some preliminary results on modeling we've been doing of the economics associated with partial harvesting. So I'm going to start with a tree. And I want to start with a tree because I think that when we're talking about carbon, it can feel a little intangible. I think probably some people on this call maybe work with carbon, maybe you do your own carbon modeling. And so you have like a feel for what I'm talking about if I start spewing a bunch of numbers related to carbon or CO2. But let's for a minute consider this tree. Imagine this is a hemlock and sort of a standard Western hemlock in a forest somewhere around Smithers that has a diameter of 25 centimeters. And if you do work with carbon modeling, or even if you don't, just hazard a guess for yourself of how much carbon is stored in this tree above ground on average. If I were in the room, I would like get a show of hands if we were in a room together. But so I estimated that this tree might have about 110 total kilograms of carbon. And if we sort of scale this up to a hectare level, we might have about 20,000 grams per square meter of carbon, or about 200 megagrams or tons per hectare. And this is equivalent to 733 tons of CO2 equivalents. And I'm mentioning that now because I just want to help like give a little sense for what that means, right? Like what does that number mean? What is it? How much carbon is that? It's not something we can see. So I put the question right here. What is a CO2 equivalent then? And so one CO2 equivalent is equivalent to maybe about the greenhouse gas emissions associated with driving from Smithers to Montreal. So thinking of it in that scale, 1 hectare of forest, that above ground carbon storage, would be equivalent to about 366 round trips, Smithers to Montreal. So just kind of keep that in your head for later. So there's a lot of carbon there. Forests offer really important carbon management opportunities. And there's been a growing awareness about this, a lot of research that's been done in BC looking at the mitigation potential available in forest management decision making. I want to make the point that BC's forest sector can be a carbon sink or a carbon source. So historically, before around 2000, early 2000s, the forest sector was estimated to be a net carbon sink. That means it was sequestering more carbon than it was emitting. But since then, emissions have increased in part due to more wildfire. And I guess this graph only goes up to 2020, but we can imagine what this might look like going into the future. So when we think about the application of forest management to climate change mitigation, conservation and improved forest management has been defined as a change in forest management that increases the sequestration of carbon over time and or decreases emissions. So management decisions that affect this or that could be used for conservation and improved forest management include reducing harvest rates, potentially reducing slash burning, and partial harvesting, which is what we're focusing on, but we will talk some about other management changes as well. And partial harvesting, in practice, it can include commercial thinning, single or group tree selection, patch cutting, a range of different intensities. So I'll explain what we're looking at in our project in a couple of minutes. Partial harvesting does have a long history in BC. And you can see from this graph, it's shown as sort of the little peach-colored section at the top. And so historically, there was even a little bit more cutting that was categorized as partial harvesting, but it still makes up quite a small percentage of overall harvesting in the province. And I'm just going to show a couple examples of recent papers from BC. So here we can see partial harvesting leaves more carbon in the stands. So if you look at the graph on the left, this is carbon stocks on the y-axis, and you can see the clear cut is the highest intensity harvest. So that's the bars on the right. And you can see that all the different levels of partial harvesting that they compared to clear cutting retained higher carbon stocks in the stands immediately after harvest, as did the uncut controls, which makes sense. We also have seen in recent research that at least some partially harvested stands can really recover lost carbon quite quickly. This figure shows results from the long-term partial harvesting experiment at Jade Creek, where there were 4 harvest treatments, so a clear cut, 60% and 30% removals, and no cutting control. And you can see over about 26 years post-harvest in the partial harvests, especially the 30% volume removal, that carbon recovered in the stand quite a bit. And some of this is due to competitive release of the surrounding trees, where their growth rates increase in response to having more access to light and the resources. So partial harvesting also has other benefits besides retaining carbon on the landscape. So it helps retain forest age structure, also intact forest floors and soils. It can maintain wildlife corridors and habitat. Partial harvesting can mimic natural disturbance dynamics and help maintain visual quality. So it's a good choice in places where that's important. But there can also be trade-offs. For example, it might be more expensive or complex or dangerous. You might have to contend with reduced harvest volume and figure out if that trade-off is okay. Equipment and methods might need to be modified. And there's a potential for more landscape disturbance if in an effort to not reduce harvest volume too much, an increased area is harvested, right? So in addition to all this, landscape scale dynamics are quite poorly understood. And so this is a big motivator for the study that we have been working on. So for the first part of what I'm going to show you, our first question is, we want to understand how forest management choices might influence landscape scale carbon dynamics and other ecosystem services. So specifically, I'm going to focus today on looking at harvest intensity. So this is the percent harvest or percent retention, whether we're partial harvesting or clear cutting. We also are looking at differences in harvest rate, differences in forest age, and residue burning. And in terms of outcomes, I'm going to focus mostly today on carbon storage and carbon flux, but also harvested volume, landscape fragmentation, and fire risk are part of our study. So for this landscape scale carbon modeling part of our project, this is our overall modeling framework. I'm not going to go into a bunch of detail about each tool that we're using, but if anyone has questions or wants to talk in more detail, be totally happy to, or look at more slides after. So we use regional data and parameters to parameterize the two models that we use. So we use the stand scale model sortie to estimate growth rates for the species we're modeling. And then we use the landscape scale model Landis2 with the extensions that are listed there on the slide to model forest growth and harvest. And then from there, we use the BC Harvested Wood Products Model version 1 to track carbon through the forest products sector. And then we calculated carbon stocks and fluxes in those systems. So I mentioned briefly in our collaborator slide that this work is a collaboration with the Gitnyao, and we've been working with Tara Marsden. When we were designing the landscape to use for modeling, we focused on the southern half of Gitnyao territory, specifically the Wilpwestlaum, which is outlined in black in the map on the left and has the cross-hatching. So this is the Gitnyao territory overall is about 628,000 hectares, and almost half of that is ICH forest. And because we were using data from Date Creek to help parameterize our landscape scale model, we focused on this southern part of the ICH MC in Gitnyao territory. And based on that landscape, we designed a hypothetical landscape that shared some traits with that landscape in southern Gitnyao territory. So this is an image of our hypothetical modeling landscape on the right. This is after 50 years of harvest and wind disturbance. And the color ramp shows the above ground biomass that remains in different parts of the landscape. So you don't need to pay attention to the details there, but I just want to be really clear that we used this square 40,000 hectare landscape for our modeling. And it's really simplified ICH MC2 forest is what we're representing. So this is an 80% Western hemlock and 20% Western red cedar forest. And then we modeled, growth, harvest, and wind disturbances for a total of 50 years. So I'm going to quickly go through some of our model scenario variables. We had two different baseline harvest rates that we modeled. So one was 0.2% of the landscape harvested per year. That was our lower rate, and that approximates the current harvest rate of the ICH in this part of Gitnyao territory. And our higher rate was about 0.6% per year, which we estimated as what might be permitted on this landscape. So put in this slide to show you what that looks like as it happens over time. So on the left, this is that 0.2% per year harvest rate. On the right is a 0.6% per year. The blocks that are appearing, those are clear cuts happening. And then the smaller patches that appear, that are not red, are those are wind disturbances happening on the landscape. So at the end of 50 years, this is what that level of harvesting looks like on the landscape. Okay, so we have those two different baseline harvest rates. And then the harvest intensities we modeled clear cut with 12% reserves as a baseline for clear cutting. And we modeled 30% and 60% partial harvest. And then we also had no harvest scenarios. So I have a little bit more information there. Yeah, so the clear cuts had 12% reserves. And then the 30% removal we call pH 30, so that's equivalent to 70% retention. And then our pH 60, that's 60% removal or 40% retention. And then you'll see in the output I show, we also have scenarios that we called pH 30 plus and pH 60 plus. And in these cases, we increased the area harvested in order to target the baseline volume that was acquired from clear cutting at that rate. So in this case, we increased area harvested or rate in order, but kept the intensity the same. And this was to understand what happens if the area harvested is increased in order to still be harvesting a similar volume. And then the last couple of variables are forest age. So we modeled mature forests starting at age 150 and older forests starting at age 300. So over the 50-year modeling timeframe, unharvested stands aged either from 150 to 200 years old or from 300 to 350 years old. And then for all combinations of harvest rate, intensity, and forest age, we modeled each scenario burning harvest residue, and then we also modeled it leaving harvest residue in stands. And a quick note about our utilization rates. So we calculated the utilization rate of material that was cut based on recent data from harvested cut blocks in the region. And it's notably lower in older forests. And this is something that's, potentially lower. Utilization rate is lower in ICH forests, especially that have a lot of older hemlock than in some forest types in BC. So I just wanted to make that point. So I'm going to show you some results from this part of the project. First, we're going to look at some graphs showing changes in system carbon pools, and then we'll look at carbon fluxes. So first, I have this figure here just to show you what the relative pool size is in a harvested and unharvested landscape. I'm going to show you graphs that basically have a single line representing the change over time of the total. But you can see that the soil and organic matter pools and below ground live and above ground live pools are quite large, right? Even, at the end of 50 years, there's a lot of unharvested landscape in most of our scenarios. And these pools up at the top here on the right-hand side under clear cut are the harvested wood products pools. So this is carbon stored in wood products and then carbon stored in landfills as short-lived products age out. All right, so I'll talk through what the parts of this graph are because we'll see several in a row that have the same structure. So this is showing output from mature forest landscapes harvested at our higher rate. We have year along the bottom, so 2025 to 2075. That's our 50-year time frame. And this is total ecosystem carbon. So this is the megagrams of carbon per hectare that are on the landscape. Most of my results will be in tons of carbon, but I find in tons of CO2 equivalents, but I find the megagrams or tons of carbon per hectare to be a little more tangible. So here we see that unharvested landscapes as well as partial harvest 30, they increased in carbon over the 50 years. Page 60, it stays about the same, and then clear cutting depletes carbon in this system over time. So now I'm adding in those partial harvest plus scenarios. And we see that if you think about this year by year, in the partial harvest plus scenarios, we're removing the same amount of biomass each year as we are in the clear cutting scenario from the landscape. But we see this partial harvesting benefit even when the area harvested is increased, and we interpret that as due to partially due to competitive release of the remaining trees and just overall higher growth rates of what remains on the landscape than if you were clear cutting the stand and then planting and starting from scratch. All right, so now we're zooming out to a more complex version of that figure. So we were looking at this lower left panel a minute ago. We had mature forest cut at a high baseline rate. But now we see our two forest ages, so mature on the left, old on the right, and our two rates, lower cut rate on the top, the 0.2% per year, and the high baseline cut rate on the bottom. And first, I want to focus on comparing this bottom left corner that we were looking at a minute ago to the lower cut rate for mature forest. And you can see here that that lower harvest rate can turn what were carbon sources or landscapes that were decreasing in carbon over the time frame into carbon sinks. So you see that at that lower rate for a mature forest is 150-year-old forests. Every single scenario, even the harvesting scenarios, saw carbon increases. Another thing I'd like you to note here from this figure is that our old forest systems have more carbon than any of the mature forest systems, even after 50 years. So that means when we cut them, there's more carbon being released. And even after 50 years of harvesting, those old forest landscapes still had more carbon than the mature forest landscapes. Okay, and zooming back into one panel again here to take a look at the impact of leaving harvest residue on the site instead of burning it. So this is that high baseline rate again, but now this is the older forest, because since we have a lower utilization rate in our old forest, this is the set of scenarios where the impact is the highest. So the difference between burning harvest residue and leaving harvest residue on site is the difference between the solid line and the dotted line for a given color. And if we leave harvest residue on site, we saw a modest increase in carbon storage up to about 3% for clear-cut landscapes. And the effect on carbon was similar to the effect of competitive release, or the benefit of pH 60 plus in landscapes. Right. So next I want to show some of our results related to carbon flux. So when we're talking about carbon flux, we're looking at the change from the beginning to the end, the sum total of all sequestration and emissions that happened in our system. And to think about carbon flux, we calculate what is called net sector productivity. So this is the net ecosystem productivity on the landscape. And then we subtract biogenic and landfill emissions, and also those losses to residue burning. So the graph on the right, the panels are laid out in the same way that they were for the previous results. We have mature forest and old forest on the left and right, and the two harvest rates. And you can see that the zero line, anything that is above the zero line, that represents a carbon sink. And whereas anything below the zero line represents a carbon source. And this is actually the only place it appears. So I'll take a moment to say we did include substitution in our modeling. So substitution quantifies, if we calculate substitution effect, that quantifies the carbon benefits when timber replaces other products. And you can see it's not a part of our NSP calculation, but we did include it in this graph. So you can see if we were to include substitution, what the magnitude might be. So if we take all those sources and sinks and we add things together, here this shows cumulative net sector productivity instead of annual binned net sector productivity for 3 points in time. For 2030, so that's 5 years in, just after just a short time, 2050, which is 25 years, and for 2075. And first, I want to make zoom in again on this bottom left panel. So this is what we were looking at early on. This is mature forest at a high harvest rate. And I put time on this list because our carbon flux outcomes really do vary with time. And depending on if we have goals for climate change mitigation, the time frame for those goals is going to determine what the contribution of forest management might be. So here you can see after 5 years, it looks like all of our scenarios actually are slight sinks. All of our landscapes are slight sinks. After 25 years, the higher harvest rates are slight sources. And then after 50 years, you can see that they diverge quite a lot. And more zooming back out to look at our overall results, we start to think about our different options for managing for carbon. So if we look at forest age in this figure, you can see that in our mature forests, a lot more different management scenarios lead to landscapes that are sequestering carbon, whereas almost any harvesting in old forests is going to lead to those landscapes being carbon sources. Harvest rate will either increase positive. If we decrease harvest rate, that will either increase positive net sector productivity, so more sequestration overall, or decrease the carbon losses over at 50 years. And then harvest intensity, again, has an impact on our cumulative NSP. And I'm going to the next slide to try to visualize this in a slightly different way. So, one finding we thought was really interesting from this is that we see this shift in the relationship between the biomass that's harvested and net sector productivity between clear cutting and partial harvesting. And so that's like represented by the difference in these two lines. So you can see that partial harvest for the equivalent amount of biomass harvested per year has a higher cumulative NSP at all levels. So our options when we're thinking about managing for carbon include reducing harvest rates, concentrating harvesting in mature forests, reducing residue burning, and implementing partial harvesting, which then leads into this second piece of our question. So over the past couple of years presenting on this work, we've been getting a lot of questions about the economics of partial harvesting. And so we decided to look more closely at that for a subset of our scenarios. And this is our research question for the second part. So partial harvesting can be beneficial for climate change mitigation. Hopefully the results I've shown you support that claim, but it is usually more expensive than clear cutting. And so we wanted to understand how the value of carbon might be able to help overcome that cost barrier. So I want to look at this sector of that graph again, and you might notice I've removed the partial harvest 30 plus, just because we didn't feel that it was realistic to actually implement that as management, because you're harvesting an incredible amount of the landscape in order to get equivalent biomass. So this is 300-year-old forests that are clear cut at that higher rate. And if you look at the cumulative NSP, so cumulative carbon loss due to clear cutting over 50 years, it's about 200 tons per hectare net carbon losses. And going back to my round trips to Montreal example earlier, so this is equivalent to the average emissions from driving about 900,000 kilometers, which I calculated, I think is about going around the Earth 22 times. Okay, so I'm going to explain our economic modeling framework now. And our team for this part of the project is a little different. Valentina Zhong from the BC Ministry is joining the project as to help with the economic side. So understand economics of partial harvesting, we're calculating net present value of both timber harvesting, and so that's this equation on the top, and development of a potential carbon project, and that's the second equation. And then we use those two pieces to calculate the net present value total of a certain management scenario. So the values that are shown in green, we're estimating these using regional data from about 2017 to 2025, trying to skip some of the anomalous COVID years. So we're using regional data to estimate these parameters. To calculate net present value of timber, we're taking the average timber price, multiply that by the volume we're harvesting, and then, excuse me, we subtract harvest costs for stumpage as well as stumpage separately. And then to calculate the net present value of carbon, we calculated the carbon savings of implementing a management approach, a partial harvesting management approach, compared to a baseline of clear cutting. So this carbon credit is the difference in NSP between the partial harvesting approach and the baseline clear cut. Then we multiply that by our carbon credit price, and we're modeling carbon prices of 0, 20, 65, 80, 100, and 170 Canadian dollars per ton. And then we subtract different costs admin cost, validation cost, and verification cost estimates associated with a carbon project. And then we add those two together to get NPV total. So I put up a table of our current model input values. And if I'm just going to state now, and we can talk about this at the end if there's time for questions, but if anyone has suggestions or additional data that they want to contribute, we would love any input. So we have gotten some input that we're working on incorporating now for our next round of this model, but I'm just going to show you some preliminary results today, and some of these numbers I expect to change a little bit. So the numbers that we're working the hardest on to pin down right now are our harvest costs for partial harvesting. So what I'm showing now is going to be model output where the cost of partial harvest is 1.42 times cost of clear cutting, and then also the stumpage charge differences between clear cutting and partial harvesting, and sort of what the baseline clear cut stumpage is. So we're working on pinning these down better. But these are the inputs for the output you'll be seeing right now. Okay, so this is the annual net present value of timber on the left and carbon on the right. And I want to remind everyone, this is for a 40,000 hectare hypothetical landscape. So on the left, you can see, so this is an annual net present value of timber. This is in the millions of Canadian dollars. And you can see our clear cutting scenario is up above the zero line. Our no harvest is at zero because there's no timber being harvested. And then all of our partial harvesting scenarios are a little more expensive than the money that's made from selling the timber. On the right, this is for a carbon price of $80 per ton. This will look different for each carbon price. But then you can see no harvest has the largest carbon savings, and then we have partial harvest 30, partial harvest 60, and the 60 plus is a little higher than the clear cutting, and the clear cutting here is at zero because it's our baseline for the carbon. So we add those two together to get our NPV total, and this graph shows that annual NPV total for a carbon price of $80 a ton. So here you can see again, here's our no harvest, our pH 30 and 60, and then our clear cut and our pH 60 plus. And part of the reason why you can see the pH 60 plus follows this pattern where it increases, right, where the clear cut decreases a little over time. So that increase in pH 60 plus is due partly to the accumulating carbon benefit over the years, the model time frame. And then if we take all of our different carbon prices and we plot them together, this is what it looks like. So first I want you to focus in on this $80 a ton price of carbon along the x-axis. So now on the x we have the price of carbon from 0 up to 170. On the y-axis, instead of being annual net present value, this is now cumulative net present value. So if you add up those annual values, this is the total value over 50 years of this management approach. So $80, this is what we were looking at in that last output. And the main takeaway that I'd like you to get from this figure is that in very many cases, a carbon value compensates for the higher costs of partial harvesting. And you can see that the break-even point with clear cutting, that's going to be the point where the partial harvest line crosses this brown line down here. So the clear cutting line is flat because there's no, doesn't vary with the price of carbon. But that break-even point is going to be where these partial harvesting lines cross that clear cut line. So above about about $30 a ton, all of our main partial harvesting scenarios compensated for the increased cost of partial harvesting. All right, so I'm going to close there, and thank you very much for listening, and I would be happy to take questions if there's some time, Dawn. And also please reach out if you have any questions or would like to see data from other parts of our project or have anything you'd like to contribute in terms of suggestions for parameterization for the economic model.